Start. So it's my pleasure to introduce the first speaker of today, who is Tom van der Bremer from TU Delft, who will tell us about his work on wave breaking and jet formation on axisymmetric surface gravity waves. So Tom, the floor is yours.
Yeah, great. Thank you for the introduction. Also, thank you for both Mario and Henrik for the invitation. So indeed, as Mario said, what I'll talk about today is wave breaking and jet formation on axisymmetric surface gravity waves. And this is work led and carried out to a large, well, almost 100% by a postdoc in our group, Dr. Mark McAllister, and experiments done together with Sam Draycott and people at various places all around the world. So this is what I'm going to study. So this, if you like, is a party trick, an experiment that's done in a round wave facility, a facility at the University of Edinburgh called FlowWave, that has wave makers all the way around the tank. So if you can see the paddles, where you can see my my pointer, 164 individually controlled wave paddles, and if they are used to create something that is axisymmetric, that is focused at the center of the tank, then this spike, what I'll call a spike, and what I've called an axisymmetric surface gravity wave, in the beginning of my talk, is created. And this is the topic of my presentation today. I'm going to try and show a video. Now, it's going to take about 2 minutes, and I suspect for many it will not work perfectly given bandwidth, but I'm going to play it anyway and see how it goes. So this is, I should say before I play this video, this is some commercial work done by the Slow-Mo guys. So this was actually meant for a YouTube publication. It has lots of views. It's less scientific, but it gives an illustration of this particular phenomenon. And there might be sound, but you might not hear it. But so I'll move to the next slide. There. So this is, as I said, this is some commercial work done by people called the Slow-Mo guys, and they have a TV or a YouTube program called Planet Slow-Mo, which they use to study science, basically in a slightly informal way. So my objective in today's talk, perhaps slightly more rigorously, is to better understand what's going on here, to better understand, if you like, the fluid mechanics of what I'm calling the spike wave, and consequently what happens in axisymmetric wave breaking. And before I get to studying this axisymmetric structure, I'd like to give a bit of motivation that places this perhaps in a broader perspective. And the motivation is provided by some work we did earlier, trying to provide a laboratory recreation of the so-called Draupner wave. So the Draupner wave is a freak wave that was measured offshore of the Norwegian coast at the Draupner platform in the 1990s. And this is considered a seminal example of a so-called rogue wave because it was measured so reliably. And if you read the literature trying to study this, then there's a suggestion that in trying to explain this, there's actually perhaps a role of so-called crossing seas. That is, seas in which there are elements of energy coming from different directions. And if you like, the axisymmetric example is really a canonical and extreme version of that. So I'll study this perhaps more realistic case for a moment, and then I'll return to the axisymmetric case later. So what we did in this particular study, we looked at the question whether this Draupner wave, this wave which was much larger than the surrounding wave field, whether it could have existed without breaking. And we looked at this in so-called following versus crossing seas. So in seas where most of the energy was going in a single direction, i.e. following seas, and in crossing seas, where there was actually elements of energy going in opposite directions. And how we did this was through an iterative procedure. We changed the paddle input signals in a systematic way so that we could ultimately get a wave that would be as tall, that would agree with the record, in fact, agree with the record here shown over a limited time window. And when we did that, when we went through that procedure, here you could see we did that for 3 crossing angles. So here you see a following sea where all the energy is going in one direction. So this is an energy spectrum with direction on the azimuthal axis. Here is a 60-degree case, and here is a 120-degree case. And in each case, what we did, we iterated the signal such that we tried to converge onto the measured offshore recording, the Draupner record offshore, measured offshore. And what we found is that in the case A, so the following case, we could not get a wave signal that was both capturing the time domain over this limited time window, as well as the steepest wave, because the wave was breaking. And if we allowed for crossing, so we increased the crossing angle, we split the energy into 2 components, then we could actually get the full amplitude of this measured recording. So here you see some numbers. So here are some down and up crossing wave heights and some wave amplitudes that we inferred from the final iteration in our sort of iteration study. And here you see, perhaps if you focus on these numbers here, these were the numbers measured in the field, and these are the numbers measured in the lab scaled. So here I'm giving the unscaled version, so rather the upscaled version, so you can do direct comparison from lab to field. And you see that in the experiments 1, which has small crossing angles, we couldn't quite get to full amplitudes in terms of height and actual amplitudes. But when we allowed for crossing, then we could get much, much closer. And visually, and this is where this will start to relate to the work I'd like to present today, is that in following seas, so here this angle was 0 degrees, all the energy was directionally spread, but more or less in one direction. You see here pictures of the wave signal in the tank, of the wave surface in the tank over various timestamps. And what you see here is you see the formation of this rolling breaker, so this standard breaking type of deep water or deepish, intermediate to deepish water breaking that happened, that basically provided an upper limit to the wave height. So the wave couldn't become any taller simply because if it did, it would break, you would have a forward or a horizontal jet, and that would limit the amplitude. So plunging breaking is characteristic of these following seas. Then we took similar pictures in crossing seas. We had now substantial differences in 2 components of the energy with a 120-degree angle between these. We then showed that we could, as I said, could get the right amplitude, but more substantially, we looked at what the actual surface looked like, and you could see here that you no longer see this forward rolling breaking, but instead we see vertical and upward jetting breaking, or indeed we see this strong vertical motion that you could see form. This strong vertical motion turns out to limit the wave height much less, and that causes these waves, whatever is the focusing mechanism, we're not going into the focusing mechanism, but at least breaking doesn't stop waves from becoming as tall as breaking does in the unidirectional following cases. So this provides motivation why what I'm going to show you now is actually physically perhaps realistic. So this is physically relevant, I should say. So this is the axisymmetric case yet again. And we try to make recordings of this, and because it's so huge and we couldn't just rely on some uncalibrated camera, we couldn't rely on gauges. What we used was a high-speed camera again, without the slow-mo guys this time, and a screen, and so we can actually do measurements of the wave amplitudes and the wave shape using camera images. And to give you a bit more perspective of what this wave actually looked like, so this is the shape of the wave for various different amplitudes. So we measure it at a huge amplitude of which we call 75, but it's just as tall as we could make it, such that we could still measure it, and much, much smaller. So we repeated these experiments across different ranges. And in the time domain, this looks very much like a focused wave group that you might ordinarily see out at sea. Remember, of course, here, there is only a radial direction. And if we think about the discrete frequency spectrum, it looks like this. So it's not a narrow-banded or a single component. This is basically the input spectrum based on linear theory we gave to the wave makers. And here are then various images you could see. So the timestamp is on the y-axis, and here are then the various amplitudes going from the smaller ones, experiments 40, to the larger ones, experiment 75, where you can see clearly the formation of this small spike at first, which then grows and gives rise to this phenomenally large spike. Sorry. So what you see here on the right are measurements inferred from these images of the crest amplitude to the tallest amplitude as a function of the linearly focused amplitude. And what we show here is that we get this red line that we compare to, first of all, this Stokes limit, so the familiar limit of a Stokes wave, the 120-degree angle that everyone who works on breaking waves perhaps cites as the canonical example of the tallest a wave could be. And we see that the waves here can be much taller. And people have studied this previously. Indeed, Mach developed third-order theory, and that third-order theory, using a Stokes expansion, is shown here. And using that theory, he derived another upper limit corresponding to wave breaking when the acceleration would hit -g, and that is shown here. So in other words, in these experiments, we can get waves that are much taller than conventional and even axisymmetric wave breaking criteria suggest. Why is that? So this black box is just the sort of the briefest summary of the literature. Stokes for a unidirectional regular traveling wave predicts there's a maximum angle of 120 degrees here. Sorry, here you could see on the right, my pointer has gone. Let me just turn back my pointer. You could see on the right, and Mach predicts for the axisymmetric setup that that angle could be 109.47 degrees. But indeed, we see much taller waves. So what's actually happening, and we looked at this for a long time, and then we found this seminal paper in, well, not seminal, not cited at all, but in completely relevant paper in the literature. We didn't spot it at first because it dealt with different fluid mechanics, we thought. In fact, it dealt with bubbles. Here you can see small bubbles from a paper by Longuet Higgins in 1983. These bubbles are penetrating, so they're floating, they're basically buoyant bubbles that go through an interface. And at the top of this interface, there is sort of, as these bubbles penetrate the interface, there's also jetting behavior being formed. There are also small jets being formed. And Longuet Higgins at the time said he could model this using a so-called Dirichlet hyperboloid. And basically he said, let's consider this to be completely inertial motion with zero gravity, zero viscosity, and zero surface tension. And he then developed a model that's just driven by the geometry and by inertia to understand what goes on as these axisymmetric jets, you could see here, these jets that we think we're also seeing in the surface gravity wave problem. Remember, these are very small bubbles, very, very different scale, also form. And you see here that the shapes that from the paper from Longuet Higgins that are associated with this. Without, there's little time, but without going into the details of the theory, Longuet Higgins showed that there is this asymptotic relationship you can develop for the angle of the tallest crest as a function of time. So this has to be the behavior in time. And he said that as soon as you've crossed the so-called limiting, but no longer limiting angle of 100, this angle which I showed here, 109.5 degrees, then afterwards the angle can become much, much steeper, and it does so in a specific way in time. So here time is some non-dimensional time. And he compared this to these bubble experiments from Blake and Gibson in the 80s and found almost a perfect fit. And he also then looked at Faraday waves. So you can see the beaker on the right. So again, perhaps different physics, but in the end, not so much. And he resonated these Faraday waves and made these Faraday waves overdriven, so really large amplitude. And he saw the same type of spiking behavior occur again. And again, he sort of hypothesized that this would be the same inertial shape that is associated with this hyperboloid, Dirichlet hyperboloid. So now we'd like to do the same, and with that, I think I'll come to sort of the end of my talk today, just giving you a flavor of what's in the paper. We applied this this equation and this sort of framework of having limiting behavior that is so fast as this thing comes into focus that gravity can be ignored, surface tension can be ignored, and viscosity can be ignored. And we applied it to our tallest measurements you can see here. And the yellow lines are the angles we estimated from these images. And indeed, when we used the scaling for tau based on the initial few images, exactly the same procedure as Longuet Higgins, we found that although it was hard to capture, this angle gamma, 2 times gamma is just this sort of so-called limiting angle. Although we couldn't see the initial behavior because it was hard to measure these angles, we saw that again the data collapsed incredibly well onto this single line. And then if we wanted to also understand the maximum crest, all we had was at the point of this I keep forgetting the angle, the 109.5 degree, if we try to estimate the velocity close to that point, the behavior of the maximum crest, so the tallest point, all it was constant velocity upwards followed by negative jet acceleration down. So the angle itself can be predicted in a model without gravity, but afterwards, all this is downward acceleration, and we could indeed perfectly predict based on an initial velocity taken at the so-called breaking onset, the point where we go through this angle and the jet starts to form, things collapse onto this line very, very perfectly. So let me summarize. So I leave a few minutes for questions and people perhaps to give feedback on this this work we've just completed. Axisymmetric surface gravity waves can be much steeper than traveling Stokes waves. Perhaps this was known, but it was made very clear in this example. Unlike a traveling Stokes wave, where we have a clear upper limit of 120 degrees, the maximum angle of an axisymmetric standing waves is not a limiting angle. It is a beginning of the formation of vertical jets, and these vertical jets, they actually follow the inertial model of Longuet Higgins using these hyperboloid shapes, followed it incredibly well. It's the same physics as you might observe for bubbles penetrating the surface and Faraday waves. And to put this in perspective, this I think is also the mechanism that could be responsible for the formation of taller waves than you might expect based on a unidirectional breaking threshold in crossing seas, like I showed in the beginning of my talk with the Draupner wave example. The only thing I think I should leave up as I sort of finish up is that we're looking to investigate this in a lot more detail. And we have been awarded funding to do so over the next 2.5 years in wave breaking and crossing seas project. If there are students and postdocs in this audience who'd be keen to work together with our collaborator, Frederick Diaz, who spoke, or at least who was replaced by his postdoc, James, earlier this week, I'd like to work on some boundary element simulations based out at UCD to try and understand in more realistic scenarios what happens in crossing seas in terms of breaking, and collaborate with experimentalists doing experiments both in Edinburgh and out in China, then please do email Frederick or myself. I think with that, I should stop sharing. And
thank you very much, Tom, for this very nice talk. So we have time for questions. So is there anyone in the audience who has any questions or remarks?
I do have a quick remark, if possible.
Sure, Maurizio.
Okay. Just by looking at your movie, I compared the results with some very old results that we got when I was in Bristol, 2000 and something, with Howell Peregrine. We made experiments on a shaking table. So we had a tank on a shaking table, and we forced it with either horizontal or vertical motions. When forcing it with a suitable vertical motion, you would get some very tall water column like the one that you have shown with we call that a top head. It was flat, almost flat. So I believe, I don't know if this would be possible with the geometry that you have, but I think that since most of the energy and acceleration in your flow after a while it will become vertical, then you could probably reproduce something similar. And so if you're interested, you can go see, there is this JFM paper of 2003, and then you can see some pictures of columns very, very similar to yours, but with a flat top.
That would be very interesting. I would really have a look. I'll have a look.
Yeah.
2003 JFM. I'll have a look.
JFM, it was, I'll give you, if I remember, yes, volume 490, pages 217, 249.
Okay, and why do you think these were top hat? Is that because of surface tension, perhaps, or?
No surface tension. Actually,
okay.
Surface tension is not really important there. It's just the way that the wave develops under this specific forcing. You have to force it in a proper way.
Okay, all right, I'll read it and I'll let you know my thoughts per email.
Okay, thank you.
Mario,
yes, sorry, I just realized. So before so Stéphane Popinet has a question, but there's someone who posted one in the chat. So the question is, did you solve the conundrum of set up versus set down in Draupner wave?
Yes, so I didn't present that at all. We have a separate paper which we look at that, and we do explain exactly why there is a set up versus a set down. It's not presented today, but we have in a 2018 or 19 JFM paper, I would be happy to send to you, Sayed. Yeah, I'll send it afterwards.
Okay, great. So, Stéphane, you can ask your question.
Yes, thank you for your very nice talk. There is a classic paper by Zeff, I think the first author is Zeff, in Nature 2000, where they restudied the Faraday wave collapsing cavity, and they show that it's a self-similar process. So essentially you can find a rescaling of the collapse. And then of course that explains the very fast jets that you observed. Did you try to see if you match this particular self-similar scaling?
We have read the Zeff paper, but we must go back. I mean, we looked at the Longuet Higgins work, but we haven't actually internalized this. We should look again, I think. We read
because that's it's a fairly generic process, the fact that it's not similar, so you would expect to find it also in your
exactly. I think that's right. I think it's the same process in all of these, basically. Just Navier-Stokes with ever. Well,
it would be very nice if you could show the rescaling. Would be a nice. Okay, thank you.
Thank you.
Hi, did you? This work reminds me of the work by Fabrice Arduin on the microtremors. When you have storms coming in different directions, so they can generate temporary standing waves that create this non-zero pressure at the bottom.
Yeah.
Do you have measurements of the of the pressure now? Because and how this maybe there would be also rogue wave tremors associated with your and it will be interesting. Yeah. Do you have measured?
Francesco, that's a very good point. I mean, we haven't got pressure sensors, but we do know, of course, from Fabrice's work and other work, and Longuet Higgins originally, that these pressures would penetrate down if things are crossing so deep. And indeed, the tank operators are a bit concerned about their floor. So they're also concerned about their ceiling, but they do tend to be concerned about their floor for exactly the reason you mentioned. I think it might be helpful for us to go and put a pressure sensor in. I think it could be interesting, actually.
I have a comment about rogue waves in crossing seas. So the Draupner wave was observed at one point in time. Yeah. So it is very likely that in the neighborhood of that point, the wave group was even larger. Yeah. So basically, the probability that I think the way you're doing the experiments and the simulation, you basically say at this point in space and time, you're gonna do the perfect focusing, is right? That's how.
Well, for practical limitations only, I fully agree with you that but we're now building a gauge array that has 100 gauges, so we can actually have spatial resolution.
Yeah.
I know you've done a lot of stereo imaging. We need to get things really precise here. So sometimes the stereo imaging isn't precise enough. But you're completely right. It's this. At Draupner, it was just measured at 1 point. That was just the way it is. 1.1 measurement.
No, it may be possible that nearby there was a larger wave.
Indeed, indeed. If you looked in my slides, then we did have another gauge, and it turned out at one gauge next to it there was a slightly taller wave. So we found exactly that.
And the beginning of the onset of breaking, what is the physics of the associated with the with the initiation of breaking, with the inception of breaking in this wave?
With this jet formation.
Yeah, what is there is some.
So there is, I mean, you read the Longuet Higgins paper and it does explain it reasonably well, is that if you just take Navier-Stokes, strip everything out, you just get and then look at an axisymmetric setup and you look at the geometry, then at some point, I mean, probably read the paper, but at some point you get infinite accelerations, infinite velocities, just because of the geometry of the problem. And I think if you could probably verbalize that a great deal, given limited time, a great deal more eloquently than I do. But I'll send you the paper, Francesco, and you. And
the modulation instability, did you see any?
No, but well, this is not deep water. Of course, we don't know what if it's 1.36 in this. But we looked at this, thinking at first, this could be some nonlinear focusing, Benjamin Fear, and axisymmetric. There is none. We get the phases right with linear theory, and we just get extra amplitude. We don't get any. We don't think we see any evidence of nonlinear focusing or modulational instability here in this axisymmetric setup.
Okay.
Yeah.
Thank you.
Thank you.
So okay, we have maybe time for another question. Henrik, you have one? Maybe?
Yeah, I mean, just maybe it's a more esoteric question, but so I mean, so if you say we were trying to sort of recreate the conditions for the Draupner wave. I mean, but it's a statistical theory, right? So it's very ambitious to say, basically you look at it's like a needle in a haystack, even if the conditions are right.
Right.
Yeah.
No, I much agree. So in some sense, we called our paper a case study because what we just said, well, there is this record in time, and what we have is around one of these extreme events, we have this. So we have nothing to say about statistics. But of course, if one did do random simulations, one built in those random simulations some breaking limits, so the waves wouldn't go any taller, then we would find that if you did those simulations, you would get more waves that would otherwise be removed by the breaking threshold. I think that's sort of the only thing we're saying here. Yeah. But no, it's a completely relevant point. I mean, we must, to say something about rogue waves, I think I removed the word rogue wave from the title, but I think to say something, you must say something about the statistics. Otherwise, it becomes a bit of a, was it right or was it wrong? And then indeed, as Francesco's point, you have to think about spatial statistics also, specifically in crossing waves, where the spatial statistics are no longer homogeneous because of the crossing.
Thank you.